All right, open up your book to section 14-6. We're on page 727 in your book, and this is titled Properties of Probability. The objective here is threefold here, really. Given the events A and B, we want to be able to calculate the following. The probability of event A and event B occurring, that is the probability of what's called the intersection of A and B. The probability of A or B occurring, that's called the probability of the union of A and B. And finally, the probability of not A and the probability of not B. Those are the probabilities of what's called the complement of A and the complement of B. All right, so let's start off with the intersection of events. The intersection of events is the set of all outcomes in event A and event B. Set of all outcomes in event A and event B. And this is denoted as A intersect B. That upside down U is read as intersection. You could also read that as the word and, but that's what that symbol means there. We can sketch what this means by using what's called a Venn diagram. A Venn diagram is where you try to visually represent what's being described here with this set. So when they say that it's set of all outcomes in event A and event B, we have to look at what are these two events have in common. So we're using these two circles here to represent the outcomes in event A, is the circle on the left. Circle on the right is the outcomes in event B, and the overlap that you see is what they have in common. So that's what actually we're talking about here, the intersection of those events, the set of all outcomes in both event A and event B. So we're talking about this region right here, if I were to shade that in. That right there is literally the intersection of those two circles. This is the intersection of events. All right, so let's talk about how we calculate then the probability of the intersection of events. There's two different categories we have to put these into. And the first one is independent events, which probably gives you a big hint as to what the second category here is going to be. But when we're talking about the intersection of events, you have, first of all, independent events. We've talked about these before. We've talked about how to count up the number of outcomes if we're dealing with independent events. Now we're talking about how to calculate a probability for independent events. So the probability of A and B, or A intersect B, is equal to the probability of A times the probability of B. The nice thing about that little formula is it's the exact same formula we learned for counting in our counting principles dealing with independent events, except that we took the number of outcomes in event A and multiplied by the number of outcomes in event B. Now we're just changing that to probability, but it's the same formula otherwise. Still just multiplying those together. The other half of the story then is, what if they are dependent events? So if they're dependent events, probability of event A and event B occurring, or that's probability of A intersect B, is calculated by taking the probability of event A occurring times the probability of event B occurring, given that event A has already occurred. Again, these are dependent events, so the fact that event A has already occurred does affect the chances of event B occurring. So the probability of event B given that event A is, that's how we read that vertical bar, and then the A that follows. That's how that's read off. The probability of B given that A has already occurred. All right, let's take a look at an example. This is the example they give us from page 727 in your book. They want us to draw cards from a deck. They say find the probability of drawing 2 black cards from a deck of cards. All right, probability of drawing 2 black cards. Right, so first of all, that means we're talking about the probability of drawing one black card and drawing a second black card. So the key word there is and. So we're talking about an intersection of events. So this is equal to the probability of drawing the first black card. And we have to multiply this by the probability of drawing the second black card. But when I draw the first card out of there, there's, first of all, one fewer card to pick from. But secondly, if that first card is black, there's one fewer black card as well. So it's times the probability of drawing, oops. It's the probability of drawing the second black card given that you've already drawn the first black card. Sorry, I'm squeezing that in there, but I'm running out of room to write all that. All right. So we just got to find the product of these two. So these are dependent events. So what's the probability of drawing the first black card? Well, half the deck is black. So that means 26 out of the 52 cards are black. So the probability of drawing the first black card on the deck is 26 out of 52. 26 cards are black out of a total of 52 cards in my sample space. There are 26 out of 52. Then we have to multiply that by the probability of drawing the second black card, given that we've already drawn the first one. So that means that there are no longer 26 black cards in the deck. There are only 25 cards left that are black in the deck. And not only that, but since I've drawn the first card out of there, there's no longer 52 cards out of there. There's only 51 cards left in the deck. So it's 25 out of 51 is the chances that I draw the second card out of there that's black. So what do we end up with here if we calculate this? Well, that first probability is actually pretty nice, right? 26 over 52. If I want to simplify this, this is just going to be 1 over 2 then, right? So that's going to be 25 out of 102, it looks like. If we want to simplify that. I guess if you want to leave it in its original terms there, 25, you can grab your calculator and plug that in there. But 25 times 26 is going to give you 650. And if you multiply 52 times 51, you're going to get 2652. Okay, so you can leave it in either one of those forms there, but there is the probability that we draw two black cards. Dependent events. That's the intersection of events. All right, let's talk about the union of events. What's the union of events? First of all, it's the set of all outcomes in event A or event B. And we denote that with A union B. That U shape there is a set notation we use for a union. You can read that off as the word or as well, but that's really a union that we're talking about. So union events is the set of all outcomes in event A or event B. All right, so let's draw this out on our Venn diagram again. Again, we're going to use circle A to represent all the outcomes of event A, circle B to represent all the outcomes of event B. And so if we're talking about the union of these two, then first of all, for event A, all of the outcomes of event A are this whole circle right here. If I shade all that in, that's that green circle right there. And if I look at all the events that are in event B, we'll do that in blue, that would be this circle right here. And I got to shade that whole circle in. Notice that there's a little overlap potentially. My two circles overlap, then there's a little bit of overlap. This would mean I'm potentially counting some stuff twice there. But that right there is A union B. All right, so how do we find the probability of the union of events? Well, it turns out these are mutually exclusive or non-mutually exclusive. We've seen those terms used before. We were talking about counting outcomes, though, than we did when we talked about those previously. We're now talking about calculating probabilities for the union of events. And so the nice thing here for us is that it's the same formula, except it involves probability instead of number of outcomes. That makes it real easy to work between these two. Whether it's probability or number of outcomes, our calculation or our formula looks very much the same. So the probability of A or B, or that would be A union B, is the probability of event A plus the probability of event B. You just add those up. Now again, mutually exclusive means that you cannot have the two events occurring at the same time. So on the Venn diagram we just sketched, that would mean that the circles cannot overlap. There would be no intersection of those two. But it could be the case that you have non-mutually exclusive events. And if they're non-mutually exclusive, that's the example of the Venn diagram we saw there, where the two circles were overlapped. So I had some green and blue that were shading the same spots. So I've counted some stuff twice. So in that case, the probability of event A or B, that's the probability of A union B, is equal to the probability of event A plus the probability of event B minus that intersection, minus the probability of A intersect B, or the probability of A and B. And the reason why you have to subtract that out is because of the fact that you have counted that intersection twice. We've accounted for those probabilities two different times, and that's obviously going to throw our calculation off. We've got to subtract off one of those calculations. That's what we're subtracting out of there. All right, so let's take a look at an example here then. So for example, it says find the probability of drawing an ace or a red card from a deck of cards. Probability of drawing an ace or a red card from a deck of cards. All right. Let's see if we can figure that out. The probability of drawing an ace or a red card. All right, the key word here is or, so that tells me I'm adding these together. I've got to figure out whether that means these are mutually exclusive or non-mutually exclusive still, but at least tells me my calculation that I'm going to do here. So I've got to find the probability of grabbing an ace out of the deck, plus the probability of grabbing a red card out of the deck. And now I've got to think of whether these are mutually exclusive or not. That's the difference between these, whether I have to subtract that other quantity out there. In other words, are there any cards in the deck that are both an ace and a red card? Well, yeah, there are. There's the ace of hearts and the ace of diamonds. So I need to subtract out the probability of grabbing an ace and a red card. And that's because I've calculated, or I've included that probability twice. When I calculated the probability of grabbing aces, I included that part of it. And when I calculated the probability of grabbing just red cards, I included that again. So we're subtracting it out because I counted that twice. Okay, so what's this turn out to be? What's the probability of grabbing an ace out of our deck of cards? Well, there's only 4 aces out of the 52 cards in the deck, so it's 4 out of 52. What's the probability of grabbing a red card? Well, there's 26 cards that are red out of 52. Again, we're not talking about grabbing 2 different cards here. This is one card we're talking about, and we're talking about the properties of that one card. So I'm not talking about subtracting off the fact that there's 1 fewer card in the deck or anything like that. This is just one card we're drawing. Draw one card, and I want to find out the probability that's an ace or a red card. So probability that's an ace is 4 out of 52, red 26 out of 52, but I've included in both those calculations the ace of hearts and the ace of diamonds. I've counted those twice. So I got to subtract off the probability of getting an ace and a red card. There's 2 cards in there that are aces and red out of the 52, so I got to subtract those 2 out of there. So what does that leave us here? 4 and 26 is 30, minus the 2 is 28 out of 52. So a little better than a 50% chance of getting an ace or a red card when we draw a card out of a deck of 52 cards. All right, the last term here is complementary events. In complementary events, are two events that account for all possible outcomes. We usually denote those as event A and event not A. So not is just saying the opposite of that. And together, this accounts for everything. The event is either going to occur or it's not going to occur. There's no middle ground there. So between these two, we're accounting for all the possible outcomes. It either occurs or it does not. Now again, we can use a Venn diagram to sketch what this would look like. I don't need two circles here though, because I only have event A that we're talking about. And the box, by the way, what the rest of that box is there to indicate is everything else that's not in event A. So when I think about all the possible outcomes, event A contains some of those outcomes. The box is the entire sample space here, so outside of that box is everything that's not part of A. So if you're talking about the complement of A, it's everything that's outside the circle but in the box. So we'd be talking about all of this region right here. You're to shade it all in. That's what we're dealing with. Not A. Outside of that circle. So how do we go about calculating a probability of complementary events? P of not A. Well, since these two events account for everything, if I were to add up the probability of A and the probability of not A, maybe I'll do that over to the side here. If I take the probability of A and I add it to the probability of not A, since these two account for everything, then in total these should add up to 1. I'm certain that either A is going to occur or not A is going to occur. And that's what I am saying there when I say the sum of those two probabilities is 1. I'm certain that this is going to happen. Either event A happens or event A does not happen. So if you just take that and solve that for the probability of not A, you end up with this formula that we got here. The probability of not A is just 1 minus the probability of A. All right, so let's take a look at an example here. What's the probability of not drawing an ace? Now you could kind of take that in a straightforward technique and actually find the probability of not getting an ace. Or the other way to think about this is in terms of the complement and say, well, let's think about what's the probability of getting an ace. If I just subtract that from 1, then that'll tell me the probability of not getting an ace. So I'm going to think of it this way, that the probability of not picking an ace, not an ace, is equal to 1 minus the probability of picking an ace. And actually, we just did that on the previous example there, right? The probability of getting an ace. There's only 4 aces in the deck out of 52 cards. So that's 4 out of 52 is the probability of getting an ace. So 1 minus that would be 52 over 52, minus the 4 over 52. That would give me 48 out of 52 ways to do that. Probability of not getting an ace. Depends on the problem that you're given as to whether or not this might be a better approach. Some problems, it's easy to just go straight forward and say, let's find the probability of this event occurring. And other times you might go, well, actually the opposite of this is easier to work with, like we just did here. It's easier to work with the probability of an ace, getting an ace, and then just subtract that answer from 1, and now we got the probability that we're looking for. All right, let's take a look at the example that they give us here on page 730. We got Kelvin and Phoebe. They volunteer at a children's ward of a hospital. The probability that Kelvin catches the mumps as a result of his visit to the ward is 13%. So let's write that down. The probability that Kelvin gets the mumps here. The probability of Kelvin getting the mumps. Kelvin gets the mumps is equal to 13%. I'm going to write that just as a decimal, 0.13. And it says the probability that Phoebe catches the mumps is only 7%. So the probability that Phoebe gets the mumps is only 7%. So again, I'm going to write that as a decimal, 0.07. So they want us to find the probability of each of these events. All right, so the first one is the probability that both Kelvin and Phoebe get the mumps. So for part A, probability of both Kelvin, I'm going to call it, just say C and, maybe I better call it CA and PH here. I've already got a P in the problem there, so I don't want to use just P for Phoebe. So the probability that Kelvin and Phoebe both get the mumps, well, that's just the product of these two. It's the probability that Kelvin gets the mumps times the probability that Phoebe gets the mumps. So that's equal to 0.13 times 0.07. I'll let you grab your calculator and punch that in and see what you got. I'll punch that into mine. 0.0091 is what I've got. 0.0091. Not a very good chance. Less than 1% chance that they both get the mumps. All right. Look at part B. B says the probability that Kelvin does not catch the mumps. Okay. Well, this is the complement that we were just talking about there. The probability of not CA. Probability that Kelvin does not get the mumps. That's the same as 1 minus the probability that Kelvin does get the mumps. And that we know is 1 minus the probability that Kelvin gets the mumps is 0.13. So 1 minus 0.13, that's 0.87. 87% chance that he doesn't get the mumps. 13% chance that he does. Again, it's a complement to meaning that there's only one, these are the only two outcomes. Either he's going to get the mumps or he doesn't get the mumps. All right, part C. C is asking the same question, but it's about Phoebe. Phoebe does not catch the mumps. So the probability that Phoebe, that's not Phoebe getting the mumps. So again, that's 1 minus the probability that Phoebe does get the mumps. And the chances of Phoebe getting the mumps was only 7%. So it's 1 minus 0.07, or that's going to be 0.93. 93% chance that she does not get the mumps. All right, look at part D now. D says neither Kelvin nor Phoebe catches the mumps. Neither Kelvin nor Phoebe. We can use the calculations we just did to help us do that. We want the probability of not Kelvin and not Phoebe. So this is going to be equal to the probability of not Kelvin times the probability of not Phoebe. Now, they didn't tell us anything about if one catches them that it's more likely the second one catches them. So we're going to say these are independent events. The probability that Kelvin does not catch the mumps times the probability that Phoebe does not catch the mumps. So Kelvin not catching the mumps, there was an 87% chance of that. Phoebe not catching the mumps, we just said that was a 93% chance of that. So again, grab your calculator and let's see what you end up with that. 0.87 times 0.93. That looks like 0.8091. All right, part E, last one here, says at least one of them catches the mumps. It's a probability of at least one catches the mumps. At least one catches the mumps. Think carefully about what that means. There's kind of a couple ways you can go about finding this. One way to do this would be we could find out the probability that Kelvin catches the mumps, but Phoebe does not pH. Or it could be the other way around, the probability that Kelvin does not catch the mumps, but Phoebe does. Or it could be that they both catch the mumps. Or it could be that they both catch the mumps, but Phoebe does. Or it could be that they both catch the mumps, but Kelvin does not catch the mumps. So again, grab your calculator and let's see what you end up with that. 0.87 times 0.93. That looks like 0.8091. All right, part F, last one here, says at least one of them catches the mumps. It's a probability of at least one of them catches the mumps. It's a probability of at least one catches the mumps. Think carefully about what that means. There's kind of a couple ways you can go about finding this. One way to do this would be we could find out the probability that Kelvin catches the mumps, but Phoebe does. Or it could be that they both catch the mumps. We multiply those together, add those up, and we can do it that way. That'd be one way to do it. But actually, the complement to this is a little bit easier to look at. At least one catching the mumps, that's the complement of none of them catching the mumps. So it's the same as 1 minus the probability of not Kelvin and not Phoebe. Again, you got a couple ways you can calculate this. You can pick whichever one makes the most sense. In some cases, though, you'll definitely save yourself some work if you think about this a little bit more carefully up front. This is definitely an easier way to do this with this second calculation. So the probability that that Kelvin doesn't catch the mumps and that Phoebe doesn't catch the mumps, well, we actually just did that, right? That was the 0.8091. So if I take 1 minus the 0.8091, what do we end up with? Grab your calculator and punch that in. What do we get? 0.1909. There we go. There's the probability that at least one of them catches the mumps. There's a 19% chance of that. All right, that right there is the end of section 14-6.